Hello. Hi there, students. I hope you're all staying home, staying safe. So here is our chapter 2, the gist of chapter 2, right? We can't be recording a 2-hour lecture, so I'm taking out the most important things that I can think of from your chapter 2.1, right? So what is 2.1? It's bearing capacity analysis. So here we go for the key points. Right, so the bearing capacity analysis that we have today was actually derived or formulated for us by the father of geotechnics, that is Carl von Terzaghi, that you can see. And actually, as I probably told you before, geotechnics or soil mechanics is a very young field. It got officially started sometime in the 50s when Terzaghi published his book, that is Soil Mechanics. Right? So here we go about the bearing capacity analysis that he's done for us. Now, first and foremost, in order to understand the bearing capacity model that Terzaghi has come up for us, is that number one, the soil that we are looking at here is a dense soil, meaning that it's a dense sand. You cannot have a dense clay, you can have a dense sand. So this soil is actually a sand. Number two, the base of the footing that you're seeing here must be rough. Okay, rough. Why? You want the friction there. Number three, you see that there is a wedge. There is a wedge or budgie that is kind of attached to the base of your foundation. Can you see here? Right. And if you notice now, this foundation is actually sitting at df. That is the effective depth from the surface of the ground. This will be the surface. So this is the depth that we are talking about, df. Right. And last but not least, this foundation that you're looking at is a cross-section of a very long foundation. What is a very long foundation? Yeah, right? That's a straight foundation. Good. Now, we can move forward to see what happens when you start to push the foundation down. When the foundation is being loaded, you see that the wedge JLK here will start to push the soil down as well. So, being a triangular thing, a two-dimensional triangular thing that you see like this, what do you think is going to happen as the soil is being pushed down? Yes, you are right. It's going to force its friend on the side, JLM, to be moving sideways out as well. So this surface that we see here, LM, is can be mathematically derived and is a log spiral curve. And this will proceed to push its friend on the upper side out, and we will have a straight line coming in MN right up to the surface of the ground. Can you see here? So it's LM, JLM, this soil mass pushing the friend on the side, JMN. And what do you think, what is going to happen to JMN? You're right, it's going to be pushed upwards. So what we see now is that there will be a little mound of soil coming up here, whereas the foundation is going down. So it's like little mound here and little indentation here. So if you think about it, you have seen this before many times out there. When something has got a bearing capacity failure, but now you know it's called bearing capacity failure, you see that it is actually the part that's being loaded going down, but the surrounding bit has got things coming up. It's like little hills, little mountains. Alright? Good. And the angle that's being formed there is phi. Okay, now that is a graphical model. Now Terzaghi has very nicely come up with the equation for us, as simple as that. There's only three components to calculate the ultimate bearing capacity of your soil taking on a foundation. The first part, as you can see, you have C and C, the second part Q and Q, and the third part is 0.5 gamma B and gamma. Before we go any further, let's take note. NC, NQ, and gamma, these are all what we call the bearing capacity factors. And do not have to cry about it, because he has also very nicely come up with the charts for you. This chart came out from equations, formulas. So if you don't like the formulas, you can do the chart. It's very easy to use. All you need to know is the phi. That is the friction angle of your soil. Say it's 25, you pull it up, and you just read off the chart, whatever NC, NQ, and gamma that you want. Right? Now let's look at the equation again. The first part of the equation here, C and C. The C is actually your cohesion, your cohesive soil strength. So if I tell you that a soil has C value, it automatically comes in your head, the soil has got clay in it. Those of you who have done the shear box test will know this. If your soil is creating or is producing a graph of tau sigma n that is a straight line, right? You do 3 tests, remember, and then you get just a straight line across. That means the soil has got no sand in it, no friction at all. Hence, it has only an intersection of the y-axis. That's why it's only C value. That is your cohesion. That's a clay. Now, let's look at the third part of the equation, 0.5 gamma B and gamma. This is the friction part. So when you say this is a friction shear strength part, that means it has got to have a value of phi. It has got to be a sense. So if in the shear box sense, you start to have a graph, instead of flat for clay, you have a graph that is going upwards. And that gradient that it forms between the graph and your horizontal line, that will be your friction angle phi. So these two components are telling us the soil type, or rather depend on the soil type. Now the middle bit, this is the one that is critical because it's Q and Q. That is about surcharge. Why? This is all because you do not put your foundation on the ground surface. Rarely do we do that because of stability reasons, right? So we always excavate to a certain depth and start to put our foundation in there. And that depth that we put it, that is actually a surcharge effect, right? Good. Now, based on the experiment that Terzaghi used to model the bearing capacity failure, these are the charts that can come out, derived from it. If you plot displacement, there's a vertical displacement going down when you load it against the load, you get two types of graph. One, there's a blue line that we have there. It's very clear. Load, every load that you apply, you have a displacement, load, displacement, load, displacement. Until a certain point, you load it, the displacement is so large that you don't need to add any more loads and you still be going down, and the soil has actually failed. So in this case, it will only happen if you have a dense soil, dense sand actually, and there's a gradual increasing displacement, as we can see here, gradually increasing with the gradual increment of the displacement with load, and then suddenly there is a failure. See, a very sharp turning, sharp cornering, and it goes right down. And this is what we term as general shear failure. On the other hand, you could have a situation where you have a plot that is going infinitely. You can't find the distinct sharp cornering like this. See the green line here? And this happens in a loose sand situation. Right? And you see that there's a large displacement. You keep loading, it keeps going down. You keep loading, it keeps going down. And you cannot find any obvious failure point. You don't see a distinct cornering like this. And in this case, you still have to tell where exactly is the failure point, and we usually put in a limiting value of displacement. So it depends. Maybe the local authority will say that, okay, for such and such a building, the maximum settlement because of the load we can allow is 250 mm. So you just put, say 250 mm is here, you put it up to the graph and bring it up. So that will be the maximum load that you can allow. That's the maximum load that you can have for the bearing capacity. And this situation we term it as local shear failure. Right? So this is important to know. Remember, dense soil situation and loose soil situation for bearing capacity pattern. Okay. Next, let's look at the equation. The other factors that's coming in to affect this bearing capacity equation. Remember, there are just three things. Whether it's about the cohesion, it's about the frictional resistance of the soil, and third bit is about the surcharge. So other people after Terzaghi started to come up with more experiments and trying to give a better explanation, trying to make it more accurate if you like. So the people like Meyerhoff, Hansen, and so on and so forth. And then they come up with 5 bearing capacity factors that could effectively make the estimation of bearing capacity more accurate, as you can see there. The shape, the depth, the inclination, the slope, and also the tilting of the footing space. So if you think carefully about it, they have covered all possible grounds that could happen to a footing when it's being constructed on site. So let's look at it. Before we move on to the next slide, just bear in mind the slightly changed form of your bearing capacity equation now. Still the same CNC, QNQ, 0.5 gamma, B, and gamma both. You have all these factors coming in now, S, D, I, G, P. So let's go through one by one very quickly what these factors are all about. Number one is about the shape factor. If you recall, the model that Terzaghi presented to us was actually about the cross-section of a long footing. So what is a long footing? A long footing is essentially a strip footing, and in such a situation, we can analyze it in a two-dimensional situation. However, if your footing has got a limited dimensions such as square, rectangular, and circular, so you need to analyze it in a three-dimensional condition. Alright, and these factors can be found in your table 2.2 in the module. The second bit is about the depth factor. So this depth factor is interesting. Remember, I told you earlier on, it's from the second part of your bearing capacity equation. Now, remember I told you we excavate, we put the foundation in at a certain depth, df, That's the effective depth. And we also remember that when you have a foundation, you load it up, it's going to form this wedge, it's going to push it out, the log spiral, and then the vertical surface going up and push the soil up. Now in this situation, you can see that this bit of the soil on the side of your foundation is going to be helpful to prevent the failure from happening. Am I right? This is going down, this is going down, going sideways, pushing up. You want to go up, I am stopping you. So this is what we call the surcharge effect, and hence how deep your foundation is and the soil condition, the soil properties are going to have an effect on your bearing capacity in a positive way actually. The third factor that we would like to look at is actually the inclination factor. So here we see inclination is all because you have a load that is not coming in totally vertically and not totally horizontally. So that is simply put a vector. So this inclined load is going to cause a resultant inclined reaction, resultant inclined load that is going to be what? Extra push to the soil to fill. I think this is logic, right? You have a load coming down from the top and having a load that's coming down on the sideways. This inclined thing is going to be more difficult to resist, right? And it's going to make your bearing capacity failure pattern more complex. The fourth factor is a ground slope factor. So the situation where your footing or foundation is being put on a slope. So I think this is logical. When you have something that is popped on the slope, whatever soil mass that is on the upper side of your foundation is going to be bad for your foundation. It's logical. And the steeper it is, right? The steeper it is, or the bigger the value of beta angle is, and the smaller your factor will be. When your factor becomes smaller, automatically your bearing capacity, resulting bearing capacity is going to become smaller. That's why from here you can see that the bearing capacity factors effectively make the calculation of the bearing capacity less risk, if you like, with lower risk and safer. And the last but not least factor we're going to talk about is the base tilt factors. Now, no matter how we carefully try to excavate, have a flat base, cast the formwork, put in the formwork, cast the concrete and all, you sometimes still end up having a tilted foundation in this case. And again, logic will tell us that having a tilted base and being loaded from the top is not going to be helpful. And the tilt, the greater the tilt, the greater the tendency of the foundation to fail on the other side of the tilt. Can you imagine that? Yep. So that is what we have for the tilt factor. Now, we move on to some solve examples very quickly. It's easy. You remember the equation we have, and this example is in your book actually. You can read the question, but I extracted the information for you. It tells us that it's going to be a square foundation, and I have it at df, that's effective depth of 1 meter from the ground surface. Can you see? There's a B, and the gamma of the soil is 18, and the phi is 35. I'm not given any C, so in a way it is implying to me that the soil is a sand, it's not the clay. So I can automatically quickly take away C and C. Okay, this will become 0. Now, very critical is that it tells me the groundwater table is very, very deep. So my foundation is not affected by the groundwater. So all I need to do now is to pop all these numbers into my equation. Not difficult, right? Q and Q, remember Q, the surcharge is gamma df, and NQ and N gamma are taken off the chart. Remember, we talked about this early on. Phi is 35, bring it up. Just read it off. What is your NC, NQ, N gamma that you want? As simple as that. Remember, this is on a log scale. Do not simply read. Between 10 to 100, there is a multiplication of 10. So this is not 15. This is what? Something like 60, 70, things like that. Okay, so you just pop that in. Same thing here for your 0.5 gamma, B, N gamma. And you get 1494. Simple, right? So now, let's look at the second part of the question. Same thing, but now look at the diagram here. There's summarize a question for you. Your groundwater table now is at the top, at the surface of the ground. So senang cakap, your foundation now is submerged in water. So what is the effect now? Having the groundwater on the surface. Now, for all the gamma of the soil that you want to use, it has to be minus off with the gamma of the water. Why? Because the water is no good for your bearing capacity. It has buoyancy effect. Alright, instead of giving more strength or more bearing capacity to your foundation, it is taking it away. Hence, all the gamma that you see, you got to minus off with the gamma of the water. Same thing here, can you see? Minus off, and you get the answer. So the last bit I want to remind you is that, look at the number here with the groundwater at the ground surface, 664. Compared to, if the groundwater is far, far away, it's 1494, is half. So see the significance of having the groundwater, how bad groundwater level can be if it's too near or at the surface of your foundation. So that's all we have about the foundation bank capacity analysis example that we have here. Alright, that's part 1 of it. Thank you.